Alright, so welcome to the screencast for objective number 8. We're going to talk about exothermic and endothermic reactions based on energy levels of products and reactants. So you're going to see things like catalysts and activation energy and energy charts come into play. So our essential question, what are the basic differences between exothermic and endothermic reactions, and how can energy graphs be created? So some thermal energy changes. The most common form of energy change in a reaction is the release or absorption of thermal energy. So we think of this in terms of heat being given off or heat being taken in. Thermal energy is heat energy, think thermometer, and we measure this by measuring the temperature. So you can tell if the temperature is going up or if the temperature is going down. Chemical reactions that change in thermal energy. Our first type is an endothermic. That means in or heat. So endo means in, therm means heat. So these reactions are going to take in heat. And because of that, the heat is absorbed. It is used in the reaction, so they're going to feel cold. Thermal energy is going to be a reactant, meaning this reaction is not going to happen unless there is some thermal energy that it takes in from the surroundings. They will feel cold to the touch. If you've ever used one of those breakable ice packs, these reactions are endothermic reactions. Exothermic reactions mean out in heat. So heat is going to be released out. Bonds are broken, so heat is going to be let out into the system. Heat is released. These are going to feel hot. We've done a couple of chemical reactions where you've touched the side of it and it's felt hot. So thermal energy is going to be a product because it's something that is produced by the reaction. So the first example here, photosynthesis. Plants absorb the heat energy from sunlight, so they take in the heat energy, and that is the energy that is used to create glucose, as well as oxygen as a byproduct. But that heat energy is what is taken in, so it is a reactant. In this example, methane combusting, heat energy is released from the methane into the surroundings. So you see heat being given off. So this is going to feel hot. And just a little joke for you, Thog makes the discovery that methane gas is explosive. So why thermal energy changes? This diagram is a nice diagram. Going from solid to a liquid to a gas also takes thermal energy changes. Like when we give something heat, when we give heat, to a system, you can get it to go from a solid to a liquid and from a liquid to a gas. So the heat is absorbed, those chemical bonds are then broken apart. You're giving them the energy to break apart from each other. If you want them to bond together, you've got to take some of that energy away so that they have to bond. Going from a gas to a liquid to a solid, heat's going to be released out to the surroundings. The chemical bonds are then going to be formed. So bonds break. When we have bonds break, they go from more stable to less stable. So the stability of the bonds decreases, and heat is required to do that. If you're going from more stable to less stable, you're going to have to give it energy to make it less stable. So heat is taken in. If you have bonds that are forming, it goes from something less stable to more stable, so heat is going to be released out. It doesn't need that energy anymore, so it's going to give it out to the surroundings. The stability goal, full outer shell. Remember, everything wants to have a full 8 electrons, except for helium wants 2. But everything wants to have full 8 electrons in its valence shell. And that is the goal. So things will react, whether it's releasing energy, gaining energy, whatever they need to do to get there. System versus surroundings is another thing you need to be aware of. The system is what is actually reacting, so where the reaction is happening. So like water molecules becoming ice, melting into ice, that's the system that's happening. That's not really a chemical reaction, but it is the system. The surroundings is everything else, so the stuff around it. This is a good diagram right here for you. In an exothermic reaction, energy is released into the surroundings as heat. As a result, the temperature of the surroundings increases. So you feel it as heat being given off. In an endothermic reaction, energy is absorbed from the surroundings, and as a result, the temperature is going to drop. So the heat's going to be taken in, and you will feel things get colder. A little bit about enthalpy. The heat energy change, which is the change in H, the triangle means change in, and H meaning heat, that takes place when reactants go to products. So think about the whole system. So this would be not the surroundings, but the system itself, the actual chemical reaction that's happening. If heat is absorbed, meaning it's an endothermic reaction, during that reaction. The change in H is positive, and so it's going to be a reactant. So you are going to have a positive change in H because you're taking it in, and the heat's going to be a reactant. If heat is being released, that's an exothermic reaction. The change in H is negative because you're losing energy, so it's going to be listed as on the product side. So that's a way to identify them, is by looking where the energy is at. If it's on the reactant side, it's going to be endothermic. If it's on the product side, it's exothermic. So here's a nice energy diagram. This is what we mean by energy diagrams. You might have seen these before. You might not have. But what this is showing you is the energy, which is measured in joules or kilojoules, versus time, just how long the reaction takes. So you're going to compare the energy level of your reactants to your products. And you can see here that my reactants have more energy, they're higher up, than the products do. Products are lower down. So I have lost energy during the time of this reaction. So this is clearly going to be an exothermic reaction. I've got this activation energy, which is what the ACT stands for, is this activation energy. That's the minimum amount of energy required to start a reaction. Remember, like striking a match, you have to give it a little bit of energy to get that reaction to go, and then it takes over. Most chemical reactions require activation energy. So a little bit of activation energy, and then the reaction proceeds to products. So I have my change in H is going to be negative because I have actually lost energy. We have talked about catalysts a little bit. Remember, catalysts speed up chemical reactions. They can be added to a reaction to increase the rate without getting consumed. So they will speed up the reaction by reducing that activation energy. So I'm going to show you a diagram in a little bit that'll show you what an actual catalyst does to the activation energy. So this is an endothermic energy diagram. You know by looking at it immediately that it's endothermic because my reactants are at a lower energy than my products are. So this change in H is positive, meaning I have gained energy. There's a lot of activation energy, but then once the reaction finally settles in products, my products are still higher than my reactants are. So they have absorbed that much energy, and that's why my change in H is positive. So I want you to draw this, because this is an example of clearly an endothermic reaction in your notes, so that you have a diagram of an endothermic energy diagram in your notes. This is an exothermic energy diagram. So we have reactants going to products. So you can see the reactants are at a higher energy than the products are. I have lost energy. So my change in H is going to be negative, and I would see this on the product side. I want you to draw this also and label the parts, so that way you have an exothermic diagram in your notes. We're going to do a demonstration with an endothermic and an exothermic reaction so you can see both of them and what happens in each of them. This diagram here is an awesome depiction of what a catalyst can do. So we're still going from reactants to products. So this is still an endothermic reaction because we're absorbing energy. My products end at a higher level. But notice the amount of activation energy has changed by adding a catalyst. This reaction does not take as much activation energy to get going, so it's going to occur faster. And the catalyst is not used up in the reaction, so it can be reused over and over and over again. So what I want you to do is just write down these examples. These are just example reactions, like this is a combustion reaction. This would be a synthesis reaction. You can go through and practice what type of reactions they are. But I want you to identify if they're endothermic or exothermic. So go ahead and remember, if energy is on the product side, it's exothermic. If it's on the reactant side, it's endothermic. But go ahead and identify what type of reactions these are. You don't need to relabel these diagrams since we've already done that. Or you should have already have done that in your notes. So we're going to do a little lab activity demonstration. We're going to do an exothermic reaction plus a little write-up and an endothermic reaction plus a write-up. So the summary for objective number 8 is template number 2.